Yeah, so I'm giving a mini course, and I'll recall what we've done yesterday, but actually today's talk is kind of independent in the sense that I'll recall what was the end of the last talk, and then I'm going to focus only on one problem that I'm going to define from scratch today. So if you haven't been in my first talk, that's totally fine, and you won't miss anything in this talk. So let's recall what we had last time. So here I'm just, for those of you who missed last talk, you can just ignore or don't listen for the next slide. So we had two problems that I described last time. One of them was called the Aldous Lyons conjecture, and it asked whether all IRSs of the free group are co-sophic, and we defined all of these notions yesterday. And the other question was called Cohn's embedding problem, and it asked whether all characters of the free group are co-hyperlinear. So these were just two questions. And I claimed that there is a decision problem that gets as input the encoding of a non-local game, and I didn't define what a non-local game is. I'll define it in the next few slides. So it gets some combinatorial object called a non-local game, and it needs to decide whether this game has value 1, okay? In this case, ZP value 1, or its quantum value is at most 1/2. Okay, that's the decision problem. And again, you shouldn't know what these definitions are, even those that were last time. And just saying this is some decision problem with respect to some values you can associate with some combinatorial object. And the main takeaway from last time, from the previous talk, was that if either the Aldous Lyons conjecture or Cohn's embedding problem are true, okay, have a yes answer, then this decision problem is decidable. So there is some algorithm that in finite time will distinguish between these two cases and will always halt. Okay, that's important. And I didn't say it last time, but the main theorem of the second paper that we uploaded recently is that this decision problem is undecidable. And how do we show it? We show the following thing. For every given Turing machine M, you can compute, actually efficiently, but you can compute the encoding of a tailored non-local game G of M such that if this Turing machine halts, so it's a zero-input Turing machine, it's just like some algorithm with no inputs. So if this Turing machine halts, then this game has a perfect ZP strategy. In particular, the ZP value is 1. And if the Turing machine never halts, then the quantum value of this game, it should be GM, right? Not val star of G. Val star of GM should be strictly smaller than 1/2. Okay, so we actually construct this mechanism. Given a Turing machine, we construct such a game. Okay. I'm not getting into it. Like, it's some form of a strategy. Like I gave a talk at the Institute, so I defined it there, but it is irrelevant to today's talk. So it's just some notion of a strategy of a game, of a tailored game. Okay, great. So this in particular shows that both Aldous Lyons and Cohn's embedding problem are false. Okay. But my goal in the next two talks is to prove an easier version of this theorem, okay, which is called MIP star is equal to RE. That's from 2019. This is due to G, Natarajan, Vidick, Wright, and Yuen. And here I will define everything, okay? So all the notions that will be here will be defined. So again, you start from a Turing machine. You generate not a tailored non-local game, but a non-local game. It's a bigger class of combinatorial objects, okay? Again, you can efficiently compute the encoding of this non-local game, such that if the Turing machine halted, then this game has a perfect quantum strategy, and if this Turing machine never halts, then the quantum strategy of this game is bounded by 1/2. So this is what I'm going to sketch the proof of in the next two lectures, and here I will define everything. So what is a quantum proof, and what is a quantum strategy, I will define, and everything would hopefully be clear. Any questions up until now? That was just like a recollection of what we've done and what is the goal of the next two talks.
So you're doing your proof?
Yeah. So I'm going to describe the original proof. The philosophy is the same, like the general structure of the proof is anyway the same, and the changes are in the details. So like the specific PCP that you use and stuff like that, and like there are like changes, but it would be hard to implement these changes, like to explain them as part of the lecture. So it's just easier to talk about their results. Their definitions are like simpler. It's easier to explain everything. Yeah. Yes, a perfect quantum strategy is stronger than value 1. What does value 1 mean? It means that there are strategies that get arbitrarily closer to 1, right? A perfect strategy is a specific strategy that gives you 1. It's the difference between a supremum and a maximum. So getting a value 1 on the node, like for a specific strategy, that's perfect quantum strategy. So in particular, value 1, yeah. No, it's just I'm going to, like, if you care about this stuff, like our new work, we can discuss it, but my main goal is to give you the ideas, and like, it's a school and it's not like, yeah. It's less important to me to describe our specific work. I think the ideas here are complicated enough. Yes?
Why GM should be efficiently computable?
So efficiently you don't need, that's why I written it. We get efficiently computable. But you just need computable. Yeah. It's a quirk of the proof that we get efficiently. We don't need it. Any other remarks? No. Great. So let's dive into it. So to that end, I need to describe what a non-local game is. And actually, Dor essentially did it for me. But I need some quirks of the way I'm going to define a quantum strategy. I need to define a non-local game in a peculiar manner, okay? And you will see. So a non-local game G is just the following data. You should think of it as just like some information that I'm giving you. And the data is the following. I'm giving you a finite set, X, which is called the question set. I'm giving you a distribution mu over X times X, so a probability distribution over pairs of questions. I'm giving you a length function, and this is the answer length function. So for every question, I'm telling you how long I expect the answer to this question to be. Okay, that's the function L. And I'm giving you decision functions. These are the dxy. And notice that the subscript is a pair of questions. Okay, so for every pair of questions, I'm giving you a function that gets as input two answers, right? We said that the length L is like what I expect to be the answer length given I ask the question X, and Ly is the answer length of the answer given I asked Y. So I'm getting two answers, and I'm telling you whether it's a 0 or a 1. So I wrote up there the field with two elements, 0 and 1, and I interpret 0 as losing and 1 as winning. Okay, great. So that's the data of a non-local game. It's just a single set, then a distribution over the set squared, then a function from this set to natural numbers, and then a collection of functions for any pair of questions such that there is a positive probability of asking them. Now, how do you interpret this data as the rules of an interaction between a verifier and two provers? Okay, so you do the following. So you have this entity called a verifier, and the verifier first samples a pair, x, y, according to the distribution mu, sends x to the prover Alice and y to the prover Bob. Great, up until now I understand what happens. Then Alice needs to reply with a bit string of length L of x, okay, which is just a vector in F2 to the Lx. And Bob needs to reply with a bit string of length Ly. Okay? And then what the verifier does is just taking the decision function dxy and evaluating it on AB. It gets either a 0 or a 1. 1 we interpret as accept, yay, a winning condition, and 0 as a nay, a losing condition. Great. So as I just said, Dor helped me and gave us the following example yesterday. So I'm just going to formalize his example in my formalism. Okay? So given a graph, gamma, a simple graph, the gain G gamma is the following. So the verifiers first samples an edge uniformly at random out of the edge set of this graph. Then it samples uniformly at random an endpoint of this edge. So it got an edge and one of its endpoints as the pair. And it sends, for example, to Alice the edge and to Bob one of the endpoints. OK, great. Then whenever the verifier sends an edge, it expects 4 bits. And these 4 bits are 2 pairs of 2 bits. OK, so A1 is 2 bits, A2 is 2 bits. And when I say send just a single vertex from the graph, I expect only 2 bits. OK, so that's the length function of this game. And then, given the decision predicate of EW given the answers A1, A2, B, maybe I'll use this. So the decision predicate given this input will be 1 if and only if the following thing happens. So I don't allow any of the pairs of bits to be 1, 1. Why? I want to encode 3 coloring and not 4 coloring. So I never allow them to use the 4th color. I think of 0, 0 as color number 1, 0, 1 is now color number 2, 1, 0 is color number 3, and 1, 1 is the 4th color that I don't want them to use. Then I ask for the edge to be well colored, right? I want the 2 endpoints of the edge to have different colors. That's the requirement that A1 is different than A2. And I want to check consistency. We think of it as if the provers have some global coloring of the graph, and they answer according to it. So the one that I asked only a vertex should be consistent with the respective endpoint of the color of the edge player, right? So this is this condition. And indeed, this is just the 3 coloring game on gamma. So whenever I get a graph, I can define this 3 coloring game on the graph. Great. Now, we didn't say, given this information and this kind of protocol, what are the rules for Alice and Bob to generate their answers A and B? And that's very important. For example, if they sit in the same room and they can communicate after they get the questions, it's very different than if they are in separate rooms and they cannot communicate after getting the questions. Okay? And we will see in a moment that if they have access to qubits, for example, entangled qubits, it gives them even more power, even though they're not in the same room. Okay, so let me describe one collection of possible strategies, like rules of how Alice and Bob can generate their answers. So a synchronous deterministic strategy for a game G is just a function that for every question gives you an answer of the appropriate length. And note that I'm not distinguishing Alice and Bob. Alice and Bob will have the same function, and that's the word synchronous here. Okay, great. And then, if I'm giving you a synchronous strategy, what is the value of the game given this strategy is just what is the probability I sample a pair of questions according to mu, that the decision predicate will give me 1, given that Alice and Bob always answer according to this function. So whenever they get x, they answer f of x. Whenever they get y, they answer f of y. Okay, so this is like the value of the synchronous deterministic strategy. And the classical value of a game is just the maximum over all deterministic strategies. Okay, that's just a definition. And again, Dor remarked it yesterday that if you have a graph, this graph is 3 colorable if and only if this kind of strategy wins with value 1. So one direction is easy. If you have a 3 coloring, it's not hard to see that you can define a perfect strategy, like a deterministic strategy for this game. The other way requires some work, but it's not that hard. Okay? But you can prove it for yourself. It's a nice exercise. But I need a larger class of strategies. Okay? So I want to allow my provers to do more than just whenever I ask them the questions, always answer the same answer. I want them to have some flexibility. And the way we do that is using what's called quantum strategies. So to define a quantum strategy, I need a few steps. So I'm going to give you the definition, but it won't be clear from the definition how do Alice and Bob generate their answers. So that will be only in the next slide. So what is a d-dimensional synchronous quantum strategy for the game? It's a function, again, that instead of associating to each question an answer, associates to each question a representation, a unitary representation of this fixed dimension D of the abelian group F2 to the LX. So again, I don't expect you to immediately see how is this generating answers, but just this is the information of a quantum strategy. For any vertex, for any element in the question set, I just associate the unitary representation of F2 to the LX. Is it clear, like just what is the object? Great. So we had, as our definition of a game, we had a length function, an answer length function that told me for any question what is the length of the answers I expect. These are many, it's like LX many unitaries. Right, like it's the same as giving me LX many unitaries for any question, but they need to commute and be of order 2. That's like the same information, right? Because a homomorphism of this form is just LX many unitaries that commute and of order 2. So we have this definition. I just popped it upstairs. And to describe to you how is this definition giving me actually the answers, like given I asked X, Y, what is the probability that they will answer A and B? I need to first recall what is the Fourier transform of a representation, okay? So this is just like a formal definition. If I have a unitary representation from F2 to the L to unitaries, then the Fourier transform U hat of A, it's again a function from F2 to the L to matrices of the same dimension. It won't be unitaries anymore. They will only be matrices. And it is defined the following way. So you take so U hat of A, where A is some element of F2 to the L, is just the expectation over all elements in F2 to the L of -1 of the dot product of A and alpha, right? Over F2 to the L, I just can take the like the dot product, the standard dot product, x1 times y1 plus x2 times 1, 2 modulo 2, times the unitary U of alpha. And I claim that if you do this operation, you don't get unitaries anymore, but you get orthogonal projections. So these elements satisfy that their square is equal to themselves, and they are self-adjoint. They're conjugate to themselves as well. Great. And now I claim that if you have this Fourier transform, you can have this probability distribution. So if I ask the provers X and Y, the probability that they will answer A, B is the following. So you take the Fourier transform of the representation at X, you take the Fourier transform of the representation at Y, you evaluate them at A and B, these are the presumed answers. You get two matrices, two orthogonal projections, you can multiply them, great, you get another matrix, and you can take the normalized trace of this matrix. Now, a few things that are completely not clear at this point. How is this a conditional distribution, right? Like for a fixed X and Y, if you run over all A and B, I claim that they are always non-negative and they sum up to 1. So it's not obvious from the definition, but I claim this is true, and this is an exercise to check. And this is just the rules of quantum mechanics when you measure according to a maximally entangled state, okay? Whatever that means, I don't want to get into it. These are just the rules of the games for us. Once they have these quantum strategies, this is the conditional probability distributions of them answering A, B, given that they were asked X and Y. Any questions about that? Yes?
We could, in principle, simultaneously diagonalize the matrices.
For any fixed vertex, yes, but not globally. That's very important. Not for all x's simultaneously. For a fixed vertex x, all the unitaries commute with each other because it's a representation of F2 to the L. But for different x and y, that's highly non-true. So I'm not claiming that u hat A and u hat x A and u hat y B commute. That's not true in general. Yeah. No? No answer? No question? Yes?
So why don't you find the quantum strategy as these orthogonal projections? Why?
As these, I could have defined it. That's what's called the PVM. And the PVM is always the Fourier transform of a representation. And it's much easier to define a representation than to define a PVM. So I prefer to define the Fourier transform and use representations.
I don't know what PVM is, but usually
The U hats.
Yeah.
That's a PVM. Yeah. I agree, but I prefer representations.
But is there a reason, like
In our proof, it's very important that you think of it also as representations because of all the ZP stuff. And I'm so used to now to this way of thinking that that's the way I present it. In our paper, it's important. In their papers, it's not important. Yeah.
You had
Right.
You had do that with the superscript X.
Yeah, so notice that the Fourier quantum strategy associates a unitary representation for every x in x. Yeah, for every x in x, and then you do the Fourier transform independently for each x, and this is like the probability distribution. Other remarks or questions? No? Yes, Alon?
Okay, so just so I understand, for your purposes here, you could have also chosen, like, instead of F2 to the L, another abelian group of order 2 to the L, like a cyclic one, and did a different Fourier transform?
Yeah, so again, for our paper, that's a bad choice. For their paper, they don't care. Yeah, so again, I'm using my notations just because it's easier for me, and if you care about our paper, these intricacies are important. For the standard MIP star, it doesn't really matter. You could take another abelian group, yeah. Because of this ZP, I didn't get into it, but all these ZP strategies, the way we define them is using like this view as unitary representations. This like plays like an important role.
So one last question.
Yeah, that's good.
What I expect. Usually there is like a joint state in the user.
So I'm claiming that's always over the synchronous strategies. I have synchronous in brackets. When you hear synchronous strategies, it's always over the maximally entangled state on the space. So taking the normalized trace is the same as saying I'm measuring according to the maximally entangled state. That's a remark for people who actually learned about these notions in somewhere else, the more general notions. Those of you who haven't heard of this, you shouldn't care. That's the definition. Okay, okay, let's move on. Great. Now I can define the value. Remember that, okay, now I have the rules of how Alice and Bob are allowed to answer to me. They choose a d-dimensional strategy, quantum strategy, and they answer according to it. So now I can ask, okay, we have this interaction protocol from before. What is the probability that in this interaction protocol, given that they are using this specific strategy, they get a 1. They get a winning situation. That's the answer. This is this val G U. So U is the quantum strategy they chose, G is the game, and it's just the expectation over choosing a pair of questions of this number. Now notice, this is just, I'll use this. This is just the probability that they will answer A and B, and this is the condition that A and B are really an accepting condition. So they will give me a 1. Okay, so it's just the probability of getting 1 in the previous interaction. Okay, great. And then what is val star? What is the quantum value of a game? It's just the supremum. This is the synchronous value of the game, okay? But everything here is synchronous. So it's just a supremum over the val GU over all possible d-dimensional U's. So notice that as opposed to the deterministic strategy, when we had a finite amount of strategies, here it must be a supremum because you can take arbitrarily large dimension of the strategies. That's very important. Like the complexity comes from there, exactly from the fact that these U's, you have no bound on the dimension of the strategies that you're using a priori. A 1-by-1, like the deterministic ones come from representations, 1-by-1 representations. Yeah. Like when D is 1, it's exactly the deterministic strategy. Yeah.
The extremal ones are
the deterministic. No. I defined only the deterministic strategies. There was no extremum. There were finitely many deterministic strategies. They are exactly the one-dimensional quantum strategies. You can check that in my definition, you can see that all the rules are such that this definition, maybe this definition, this F is the same as taking a one-dimensional quantum strategy. That's my claim. It's the same thing. There is no convex combinations. I didn't take any convex combination. It's just a deterministic thing. Yes?
Is the supremum over all choices of D?
All these, and then all representations associated to each, right? Like I'm choosing an D, and I'm choosing as many unitary representations of size D of F2 to the LX for every X in X. So it's a lot of information, but okay, it's, again, like some collection of matrices, right? Yeah? Great. Great, so that's a remark, okay? So there are graphs such that their deterministic value is strictly smaller than 1 in the coloring game. In the 3 coloring game, the deterministic value is strictly smaller than 1. Namely, there are not 3 colorable, but the quantum value of this game is 1. So in some sense, you can define what's called the quantum chromatic number of a graph. And a priori, the quantum chromatic number of a graph can be strictly smaller than the actual chromatic number of the graph, which is very nice. Like there are many people who spend a lot of their research time studying these kinds of questions, okay? You like take a classical question, you translate it like a combinatorial classical question, you translate it to a game, and then you ask questions about the quantum value of the game, and like you get new quantities that are interesting, okay? So for example, the quantum chromatic number. Great, now the first person who gave actually a game, a non-local game, such that the quantum value is strictly larger than the value, the deterministic value, is John Bell, and he's a very renowned physicist, okay? And this was like a huge breakthrough. It's like the resolution of the Einstein-Podolsky-Rosen paradox, if you heard of it. And like that was a very important thing in the time. And actually, the 2022 Nobel Prize in Physics was given to Aspect, Zeilinger, and Clauser. And Zeilinger, we heard of him yesterday by Dor, the GHZ game, the Z is Zeilinger. And they actually like did experiments in labs and suggested experiments that were run that actually showed that in our physical space, you can achieve values that are strictly higher than the deterministic value and that approach the quantum value. And the takeaway is, in some sense, that our world is not governed by classical mechanics, but by quantum mechanics. So entanglement is a real thing. Okay, that's like the takeaway of this. Something that we really have in our physical space.
So Bell inequalities are like values on the value?
Exactly. A Bell inequality, like breaking a Bell inequality, is exactly winning better than the classical value of a game. Yeah, that's exactly a Bell inequality. More remarks or questions? No. Okay, great. So now we can parse, finally we can parse the theorem that I stated that we need to find, like resolve, right? Like now we need to translate somehow a Turing machine M to a game GM, and we know what a perfect quantum strategy is now, and we know what is the val star, the quantum value of the game. It's bounded by 1/2. So now we can at least parse the theorem that we're trying to prove. Great. And note that, like, I'm doing a computational problem, right? Like, I need to start with a Turing machine, which I think of, I don't know, as the Python code of some algorithm. That's how I think of it. And I need to translate it to an encoding of a game. So I need to choose, how do I encode games? Okay, so there are many ways of doing that, but I'm going to choose a very specific way, which is important. And if I'm choosing a different way, it's like I don't know how to prove the theorem that I want. Okay, so now I'm going to talk about encodings. How do we encode a game? So instead of encoding one game, we encode a sequence of games. And that's very common in computer science. Like you think of a single Turing machine that for any input n gives you like an instance of the thing that you care about. Okay? So this is uniform generation. So a sequence of non-local game Gn is said to be uniformly generated if there exists a Turing machine V that given an input n simulates Gn. Now, I didn't write what does it mean to simulate, but you should think of V. I didn't even tell you how many inputs V has. So, for example, you can think of V as having, I think, 6 inputs is enough. Okay? So you take V, and, for example, I put n, and I tell it to sample, and I don't tell it anything else. So the other 4 inputs are blank. In this situation, I expect the Turing machine to be probabilistic, and to output to me 2 vertices in the game. Okay, so it will output 2 bit strings, and I expect x and y to be just the vertices in the game Gn. Okay, and then I can ask, okay, maybe Vn length x dot dot dot, or something like that, In this case, I expect the Turing machine to give me L of x in the nth game. Remember, like there's the answer length in the nth game. So, for example, given this input, I expect the Turing machine to give me just a number. Okay? And lastly, if I want to give it decide x, y, a, b, then I expect it to tell me in the nth game if the questions were x and y and the answers were a and b, should I accept or reject? Like it should give me a 0 or a 1. So that's what I mean by a Turing machine that somehow uniformly encodes a sequence of games. Okay, is this clear? Great. Now, I say that this sequence is lambda efficient if all of the simulations, so all of these, like, no matter what is the command that I give it, sample, length, or decide, it will run in n to the lambda time. Notice that it is independent of x, a, y, b. Okay, that's very important. Like, the running time is independent of, like, maybe these bit strings are very, very long, and then d will not even read them, right? But in that case, it probably will just reject it, right? Because it was a too lengthish of a bit string. Okay? Like that's the way you should think about it. But it's important that the efficiency depends only on n and not on the other inputs. Okay, great. So again, those of you who know like the definitions of PCPs and IP and stuff like that, like it's clear, right? Like you don't want to depend on the proof. You want to depend only on the input, like the running time. Okay, that's a good point. So potentially I can give you a Turing machine V that for certain ends never halt. Okay? And then there is no really Gn. Like for this specific nth input, there is no real G there. There's no real game there because the Turing machine will never halt. But I'm not getting into these intricacies. That's true. That's very important even for us. But let's not get into it alone. Yeah,
but the lambda efficient, like it halts?
Yeah, if for lambda efficient, it always halts and it always defines a game. So when it's lambda efficient, really for any coordinate in the sequence, there is a game there. V is a Turing machine. Yes. It has a code. Yes. There is the length of the code. So I also ask the length of this code to be bounded by lambda. Okay? So that's, yeah, I didn't remark that. Yeah, the last condition there is that there is also some bound on the length of the code when I ask something to be lambda efficient. Let's move on. Great. So I need a final definition before I explain to you what is compression. Okay? So the main tool in MIP star is equal to RE is what's called the compression theorem, and I need one last definition before I go there. So the entanglement lower bound of the game G with parameter theta, so this parameter theta is just a number between 1 and 0, is just the smallest dimension D such that I can win in the game G using a D-dimensional strategy with probability at least theta. So this number can be infinite. For example, if I give you a game and you cannot win with probability more than 2/3, if I ask for the entanglement lower bound for 3/4, it will just be infinite because no quantum strategy achieves that. But it can be infinite even if, for example, we saw before, we said that there are games, okay, at least in the previous, when we talked about subgroup tests, we said that there are games with value 1, but no specific strategy that gives you 1, right? So again, even in this case, the analog of entanglement lower bound will be infinite if you put the 1 there. Okay, so it's a subtle thing, and I ask for a specific strategy that gives you that. No remarks, great. So now I'm giving you the compression theorem. Okay. So there exists a polynomial time algorithm, which is completely fixed. It's called compress, and it has the following properties. It takes two inputs. One of them is a Turing machine V, which uniformly generates a sequence Gn of games. And it takes also as input, note that this is important. Let me highlight. And it also takes as input a natural number lambda. Okay, so it has two inputs. And it outputs a new Turing machine V prime that should should uniformly generate a sequence of games, a new sequence of games, okay? And we have the following properties. So we have 4 properties of this Turing machine, okay, this compressed Turing machine. So first of all, the question sets the distributions mu prime and the answer lengths L prime depend only on lambda. So we had two inputs. We had V and lambda as input. In the new uniformly generated sequence, the sampling mechanism and also the length functions are independent of the original V. Okay, so in the language of the previous slide, if you take compress V and you run it on n sample, compress V lambda, and you run it on n sample, the answer is independent, like the mechanism is independent of V. It will always act the same way, only depending on lambda. Okay, same for this. So for compress V lambda, the length function of the vertices is independent of the original Turing machine. And this is very important. Okay, so this is the independence condition on the new Turing machine V prime. The second condition is that this new Turing machine, even if the original Turing machine never halts, that's very important. Even if the original V, for every n, none of the commands halts, okay, like that's possible. Still, this new Turing machine is very efficient. There is some polynomial, there is like a global number C such that it never runs more than Cn to the C plus lambda to the C steps. Okay, that's what I mean by poly n C, poly n lambda here. And this C is completely like universal. Now I'm going to give you two conditions, and these two conditions are only when the original V was lambda efficient. Notice that I just gave you two inputs, right? I gave you a V and I gave you a lambda. There was no connection between V and lambda up until now. Now I'm giving you some assumption. If this V was lambda efficient, then two extra things happen. Okay? So maybe I'll say it out loud before I tell you. The point is that if the input was well structured, if the input was such that V is lambda efficient, then this new uniformly generated collection of games simulates the old one exponentially faster. Okay, somehow the nth game here is analogous to the 2 to the nth game of the original sequence. That's the notion of compression. Somehow I get exponential speed up in some sense. Like I'm able to simulate the exponential game. So, but that's only when V is lambda efficient. And what do I mean by exponential? Like by simulate, the following two properties. The first is completeness. If the value of the origin of the 2 to the nth game, if the value of the original 2 to the nth game, which was uniformly generated by V, had value 1, then the nth game of the compressed Turing machine has value 1 as well. Okay, that's the first condition. That's the completeness condition. And the second condition is some soundness that I'm encoding as a property of entanglement lower bounds. Okay, so I'll say it out loud. The entanglement lower bound of the nth game of the compressed thing, okay, is at least the entanglement lower bound of the 2 to the nth game of the original one, the maximum between that and 2 to the n. Okay, notice that here, that's very important. That's independent of the original verifier as well. Like, okay, the verifier needs to be lambda efficient, but this condition is independent of the specific verifier, of the specific V that encodes uniformly. I call these the Turing machines that encode uniformly, I just call them verifiers, okay? Like, that's a common name. That's why I also write V. Yes, that's a good time for questions.
Can you repeat the definition of entanglement? Like, what are you trying to measure? What is entanglement really is?
The smallest dimension D, such that I can win this game with probability at least theta if I use a dimension D strategy. There exists a dimension D strategy such that I can win the game with probability at least theta if I use this strategy. So in the case of 1/2, here I'm using only 1/2. So I ask, how many dimensions do I need? Like, what is the dimension size that I need to win the game with probability at least 1/2? The answer is whatever the 2 to the nth original game gave me. But no matter what was that, you at least need 2 to the n dimensions to win this game. And this comes from representation theory. We'll see it like next lecture. Like this number.
So it's like the complexity of the game, in a sense.
It's how hard is it to win this game? If you want to win it with probability at least 1/2, that's the question. And the measurement of how hard is what is the dimension. Like you think, in physical space, the dimension of the unitaries is the same as the amount of qubits. Okay, so you want to say, I need many qubits to win this game. That's like essentially what this measures.
Amount of randomness.
What?
Amount of randomness.
I didn't understand. This is entanglement. That's not randomness. It's analogous to randomness, maybe, if you allow like public coin flips or something like that. But like that's the quantum version of it. Yes?
Can you maybe say a word on why independence is a...
That's extremely important. Without independence, everything breaks. Yeah, I don't know, like, it's small things that when I first read their paper, like, they didn't emphasize enough how much it is important. And it took me kind of a long time to understand how much this is important. So independence is extremely important because the way you use compression, like, you don't get anything if you don't have independence. That's extremely important.
Just to
like,
make sure that the questions, the new questions, sample,
like,
sample,
yeah, the only thing that, whenever you compress a game, whenever you compress a verifier V, the new games look identical except for the decision predicates. The decision predicates may be different, but the vertex sets, like the collection of questions, the probability distribution over questions, like the length of expected answers, all of this is fixed. It's independent of the input, except for lambda. Like there is this parameter lambda, yeah, but it's independent of the V. It depends only on the lambda. That's extremely important. Yeah. Yes.
How should we think of the soundness? Like it says that you need to search like.
You should think of it as you should think of it as follows. That's easy to say. It is as hard to win the nth game with probability the new nth game with probability 1/2, as it is to win the 2 to the nth game with probability 1/2 in the measurement of how many qubits I need to use in the game. So this this dimension D is analogous to how many qubits you need. Okay? So like this is just a measurement of how hard do I need to work. Like how many qubits I'm using, it's a measurement of how hard I need to work.
So the Gn prime is hard.
Is at least as hard, so Gn prime is at least as hard as G2 to the n, and even some parameter which is independent of the G2 to the n.
Crucially grows.
And that crucially grows, that's also true. We will see how do we use it. Yes, Tal.
So it seems you're ignoring all of the games except the powers of 2, so why would you input them?
That's just like, yeah, like I'm simulating only the powers of 2, that's true. And it's enough, you will see that I don't need more than that. Like I have a goal in mind, right? I want to prove the MIP star is equal to RE. So we will see that I'm going to use this compression theorem to translate a Turing machine to a game. So we will see how, in a moment how I do that. Yeah. Yes?
Is this entanglement parameter always finite?
No, I said that it can be infinite. If you cannot win the game with any D-dimensional strategy for any D with this parameter, clearly it's infinite. Yeah. Yeah, I remarked it at some point. Okay, let's move on. Great. So now you see the headline is compression implies MIP star is equal to RE. So I'm assuming that we proved that there exists an algorithm that has all these properties, okay? And I'm going to show you that if this is true, I can translate any Turing machine into a game such that if the Turing machine halts, this game has value 1, and if this Turing machine never halts, then this game has value at most 1/2. That's the goal. Great. So you start by defining a very peculiar 8-input Turing machine. Okay, that's step 1. Let's go over first what are the inputs to this Turing machine. So the Turing machine expects an 8-input Turing machine as its first input, but that's okay, right? Like a code can take the code of another algorithm as input. That's okay. Similar, it takes another Turing machine as input, but this Turing machine has 0 inputs. It takes 2 natural numbers, lambda and capital N, and it takes 4 bit strings, X, Y, and A and B. Okay, so it's just, I told you what are the inputs, how do I expect the inputs to be structured. And this Turing machine F does the following 5 steps. So let's follow the 5 steps. First, it ignores all of its inputs except for M and capital N. So this shouldn't be small n, this should be capital N. And it runs this Turing machine M for capital N many steps. If the Turing machine halted, it will output 1 no matter what the other inputs are. Okay? So that's the first step. Then, I need to fix it now in every slide. It calculates the code of the following Turing machine. Again, it's a Turing machine that eats other Turing machines, the codes of other Turing machines, but still you can just calculate what is like the encoding of this thing. I think of it always as a Python code. It's very helpful for me. So you just calculate the Python code of taking the Turing machine R, which was part of the input. Oh, I wanted to use the... was part of the input. You take this Turing machine and you hard code these 3 inputs into this Turing machine. And now instead of having an 8-input Turing machine, because you hard coded 3 of the inputs, you now only have a 5-input Turing machine. And this new Turing machine, I just call it D. And this D clearly depends on R, M, and lambda, but not on the other inputs. Now I'm defining it to a verifier. So this verifier works as follows. It uses the same question set, sampling mechanism, and answer lengths as the output of compressed lambda. Now, recall that I said that all these objects, the sampling mechanism, the question set, the length function, is independent of the first input. So you can calculate it only using lambda. Okay? So that's the first thing, like the new verifier that encodes the uniform sequence of games has just the same sampling mechanism and length as the output of compress anything lambda. And the decision predicate is just controlled by D. What do I mean by that? Like if you want to decide whether to accept or not, you just take this peculiar Turing machine. It has 5 inputs. You put at the first input N, then X, Y, A, B. And that's like what takes the role of the decision predicate in the nth game. Okay? So I hope it is clear. It's a bit convoluted, but that's just a new verifier that encodes a uniform sequence of non-local games.
So, sorry, could you repeat 3 again?
Yes, I'm not giving all the information, like I'm doing it kind of hand-wavy, but I'm defining to you a verifier, so something that encodes uniformly a sequence of games that works as follows. The sampling mechanism is the same as whatever compressed lambda gives you. Also, the length of answers is the same as what compressed lambda gives you. And I said that's the independence thing from before. It's independent of the first input, so I can just calculate from lambda how should I sample in the nth game, what are the vertices in the nth game, and what are the lengths in the nth game. Like that's what compress gives me. But the decision predicate, whenever I want to decide whether to accept or reject X, Y, A, B, I just run this specific Turing machine, and I put N here, X here, Y here, A here, and B here. And I'll get the answer of whether I want to accept or reject. Because I have independence, I can define to you a uniformly generated sequence of games in such a way that it has the sampling mechanism of whatever compress will give me, given that the second input was lambda, no matter what was the first input. That's where I'm using independence. Okay, that's extremely important. Like I don't care what is written here. You can just put an empty string here. Calculate still what is the vertex sets, what are the length functions, and what is the sampling mechanism in the nth game. That's extremely important. Yes?
What is the purpose of M? To get some diagonalization or something?
Wait. M, this capital M, this will be the Turing machine that I want to check whether it halts or not. That's why I did the first step. We don't see it yet. I'm not in the reduction yet, but it will play the role exactly of the Turing machine that I want to check whether it halts or not. Yes?
By D means...
Now you want to decide whether in the nth game, X, Y, the questions X and Y, and answer A, B are in accepting condition or not. You just run this machine. Maybe this machine will never halt. That's okay. We said that maybe it doesn't really encode the game. That was Alon's question. But it's still, like in the formalism that we actually have here, it's okay. I didn't finish yet the running of this thing. I'm just defining a new Turing machine. For now, you don't know what R. R is an 8-input Turing machine. You started with, I'm defining a Turing machine F. This Turing machine took 8 inputs. The first input of this Turing machine was the encoding of an 8-input Turing machine. And if you have an encoding of an 8-input Turing machine, you can take it both as something that you want to run and as one of the inputs of itself. That's okay. That's like self-reference. That there is a fixed point theorem coming up. Okay, like that's where we're heading, and exactly you see it here that we're aiming to some fixed point theorem. So let's do the last two steps. We have now a verifier V. I can run compression on it with the parameter lambda. So remember, I have this lambda here. I don't need to invent it. Just run compression with V and lambda. Great. I get some new V prime that encodes some new sequence of games. And then I'm saying that this whole Turing machine, this whole F, will output, so it either outputted 1 in the first step, or it will output 1 in the last step, only if this is some game. And notice that we said that the output of compression has bounded running time. So with the Remarkov alone, it does define a game no matter what was the index, as opposed to V that maybe doesn't halt, right? Like we said, that V may not halt. But compress of V lambda will always halt because it had some upper bound on its running time. So it will always encode some nth game, capital nth game, G prime n. And I can just ask, is this quintuple, like I take this as the index of the game, will this quadruple be accepted by the capital nth game of the compressed verifier? So I answer 1 only if this is true. And the point is, everything is efficient here. I can just run the capital nth game, and I can calculate it and get some answer. It's either accept or reject, and I will answer either 1 if it accepts and 0 if it rejects. Controlled by D means you want to ask whether x, y, a, b are accepted by the nth game. You just put n, x, y, a, b. If you get 1, you interpret it as accept. If you get anything other than 1, you interpret it as reject. And if it never halts, the nth game is not well defined. So everything, there should only be one small n. All of these should be capital. I changed it along the thing, but except for this, which should just run over all natural numbers. Yeah, that's why I changed it to capital N, but too late and then. Efficiency. The runtime of V prime is polynomial in n and lambda, independent of everything. I didn't say anything about the conditions. It's always polynomial in n and lambda. That's extremely important. Yeah. Okay, great. So now let me explain to you how do you create the game. So we're not there yet even. I just defined a weird 8-input Turing machine. Okay? So given a Turing machine M and the parameter lambda, again, I have this lambda. We will fix it in a moment. Okay? We defined a verifier that depends only on MM lambda and encodes uniformly a sequence of games, such that, again, the sampling mechanism and the answer length are just whatever compressed lambda gives me. So that's, again, I use the independence that I don't need to care about the first input. And the decision predicate, similar to before that we had like this D, I'm claiming that the decision predicate is controlled by this weird 5-input Turing machine. So you take F from the previous slide, you take it both as the Turing machine that you want to run and as the first input, and you fix the second 2 inputs to be this M and this lambda. So this is now a new 5-input Turing machine. You can run, if you want to know whether X, Y, A, B wins the nth game, you can just run N, X, Y, A, B in these 5 inputs. Okay? So this is like a new normal form verifier, and again, like the reason I'm using F and F is exactly for some fixed point theorem that we will see in a moment. Okay, let's just recall what we've done here next time. Maybe I'll just say this, and I will just assume that we have these properties, okay, next time. So I claim that if you do all of this thing, you can calculate only some number which is polynomial in the description length of M, such that this VM lambda is lambda efficient. That answers your question. Okay, there is a lambda, which is just some polynomial in the size of the input M, such that VM lambda is lambda efficient. If this M halts in n step, the value of the game is 1 for any M greater or equal to the number of steps in which it halted, just because, right, the first step was give me a 1 if it halted in n steps. That's the reason for this property. And the last property, that's exactly the fixed point theorem. The game Gn and the compression of the game at the nth place are the same game if it doesn't halt in n steps. Okay? That's extremely important. If the Turing machine M did not halt in n steps, this game and this game are genuinely the same game. They have the same question, the same answer, the same sampling mechanism. That was easy, right? We chose them such that they have the same question set, the same answering mechanism, the same blah, 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 blah. The only potential difference is the decision predicate, but because we did all this work, we have a fixed point theorem that tells us that it is genuinely the same game. That's it. So let's stop here. Sorry for taking too much of your time.